So let us see now the formation of three-dimensional matrices. So here I have already written a program. This is a kind of three-dimensional matrix formation you can see here. So here what I do, I write A, where I want it to be treated as a three-dimensional matrix, and then there is a round bracket. Within the round bracket you can see colon comma colon. So that means all rows, all columns. So this first column means all rows of A, comma, all rows of A, comma, then it's first slide, or you can say first page number. So we were discussing that yesterday regarding page numbers, right? This kind of slide we had discussed, this one. So here we say that this is the first page, right? And then there is second page or second slide, and then there is third slide. So this is a kind of indices which are used in three-dimensional matrices. So here there is a third index over here, right? Everywhere you can see a third index, which is 1 for first slide, everywhere in the first slide. And for the second slide, the third index is 2 for all the elements, and for third slide the third index is 3 for all the elements, and so on. So here what we do, we specify the first slide by writing 1 over here, and then as usual we define a two-dimensional matrix. One slide in itself is going to be a two-dimensional matrix only. Then the second slide is added this way. We write 2 over here, then we add the second slide over here. So let us see the effect of the statement up to here. So for that I write Z over here, Z, and then press F5. So here you can see this is the effect. Till now it is a two-dimensional matrix only, because the third dimension, in third dimension one more slide needs to be defined. So I have just defined one slide. So now I will define the second slide also. So for that I copy this Z from here, paste it here. Now press F5. So here you can see first A was defined, and after that second slide of A was defined as 10, 20, 30 onwards, right? And since I have not put a semicolon here, so it will give me complete value of A. So it will show me the first slide also and the second slide also. Now for defining the third slide, I simply write A bracket, round bracket, all rows, comma, it's all columns, comma, third slide, bracket close, that is equal to this. This is the third slide which I want to be included. So I copy this, cut this control Z from here and paste it here. Now press F5 to see what has happened. First it defined A as a simple 2D matrix, then it defined the second slide of A, right? So after defining, it also showed A first slide, then second slide. Then over here it defined the third slide of A, and after that it showed complete A. So it repeated this, showing this A1 first slide, and then second slide, and then third slide. So first slide is containing 1, 2, 3. Second slide is containing 10, 20, 30 onwards, and third slide of A is containing 100, 200, 300 onwards, right? So this is how we define three-dimensional matrices. You can use for loops also sometimes in finite elements to define the three-dimensional matrices, where instead of this 1, 2, 3, sometimes we make use of the for loop parameters, like you can define I, J, K, where I is varying from let's say 1 to 10 or 1 to 100 or 1 to 500 and so on. J can also vary. So that kind of thing can be done very easily using Matlab and using for loops very easily. So now we go to the four-dimensional matrix. And based upon a similar pattern, it can be generalized to n-dimensional matrix also. So let me make these statements as comment. So I type Control R to convert these into comment. Now I press F5. So here you can see what has been defined. A B matrix has been defined. Let me convert this also as a comment. This we will discuss later. Now at present we are only discussing this statement. Now pressing F5. So this is a four-dimensional matrix. So here you can see I have defined B, then round bracket, then it's all rows and comma, then all columns, comma, then it's first slide. And within the first slide I have further slides also, sub slides you can see. So within the first slide I define the second sub slide as this. I want the second sub slide to be this. So you can see the output over here. I haven't added a semicolon over here so that I can see the output in the command window. So here you can see this is the first sub slide of first slide. This is first sub slide of first slide of B, and this is second sub slide of first slide of B, right? So this has now become a four-dimensional matrix. So within the third dimension we have added one more dimension, one more you can say sub dimension has been added. Within the third slide a sub slide kind of thing has been added. So this is a four-dimensional array. Although this will not be used in this particular subject, but still, because I had told you initially that we will discuss multi-dimensional array, four-dimensional arrays also. So just for introduction purpose I have shown this also. And if there is n-dimensional array, you can increase the number of dimensions as you want by playing with the indices over here. Okay, now let me make this also as a comment, and now we will see something related to functions. So Control T, I am typing Control T over here. Now I am pressing F5. So what happens? So first I defined x is equal to 10. This is a very simple function, and any complex function, whatever complexity can be there, but ultimately it is going to be defined in the same manner which I am going to discuss now. In the finite element model program which I had shown you earlier, there you must have seen that, you must have noticed that when I pressed F5 I was able to see mode shapes, everything, plot graphs were visible, but the main code of the program was not shown that time, right? Because that was written as a function separately. So we will first see how a function is written. So here I am accessing a function. Let's see how do we do that. I write x equal to 10. This is first input and that is shown over here. Then I say y equal to 20, right? Then I use this thing. So this statement, what it does, it sends the compiler to this function, first function, wherein x is treated as first input, y value is treated as second input, and the output of that function gets stored in z. Now let us see what that first function is. So here I have already prepared a first function for you. Whenever you write a function file, you always start with the keyword function over here. You write function at the starting, and here you can see its color also that has been that automatically it changes to blue. So this blue colored function word tells me that this is not a .m file. .m is the program file in Matlab. This is not a program file. This is a function file. So here the nomenclature is that first I write use a square bracket here. Within the square bracket I write whatever output I want to take out that. take out from that function. So here I am writing it as output underscore 1. There can be many outputs, so you can write comma output underscore 2, output underscore 3, and so on. Whatever output you want to take, you can mention it over here. So first I mention the output variables here within the square bracket. After that I put an equal sign over here. Then I write the function name, first underscore function, and then within the round brackets I mention the input values, input variables, input underscore 1, input underscore 2. There can be any number of inputs, right? So here this is a simple sum function. You can see I have defined a kind of sum function. So here I am saying that output 1 is equal to input underscore 1 plus input underscore 2. Simple, very simple basic sum function is defined manually. So then I save this program, save this function within the same folder wherein I want to use it, within the same folder. So then I go back to my main M file. Now I press F5. So here you can see X is defined, Y is defined, and then that particular function is called. And that function is called by giving these two inputs 10, 20. So this function is called here, this becomes 10, input 2 automatically becomes 20. Then over here it becomes 10, this one becomes 20. So 10 plus 20 is calculated, that is 30. It is stored into output variable 1, output 1 of that function, and that is transferred out of the function to the main file, and it gets automatically stored into Z. Now I want to see Z also, so I simply write Z over here without adding a semicolon here, and when I press F5, ultimately finally I get the value of I am able to see the value of Z also in the command. Okay, these are some of the, now we are about to go to the finite element modeling. So before that, there are some very basic commands which we will see. This is a format command. So here you can see these all are same values, right? 290 by 7 over here, 290 by 7, 290 by 7, 290 by 7, everywhere. But the answer format is different. You can see here, here it is a short format, here it is a long format, here it is a short format in E format, short E format. So E means E plus 001 means into 10 raised to the power 1. So here it is a long E format. So here E plus 001 again, that means, that doesn't mean E raised to the power 1. That is into 10 raised to the power 1. And this is a short G format, this is a long G format, and this is a bank format up to 2 decimal places. And similarly there are other types also. You can make the format as compact or loose. Then you can use sqrt to calculate the square root. Nth root can be calculated using this command. Exponential can be calculated using exp. abs to find out absolute value. Log to find out natural algorithm. Log 10 to find out base 10 algorithm. Okay, then sine to find out sine value when angle is in radians. And if the angle value is in degrees, then you use sine d. Similarly, you have other terms like cos and cos d, tan and tan d, cot and cotangent d, cot d. Then you have round to the nearest integer. Fix is to round towards 0. Seal, it is also used in MS Excel, this kind of keyword formula, seal. So seal is sealing basically, you can say roof, right? So rounding towards plus in positive infinity. Floor is, right? Floor is rounding towards or rounding towards minus infinity. REM, REM is to find out the remainder. Like if you divide 13 by 5, the remainder will be 3, and that is obtained through the command rem. These are the basic rules for defining variable names and functions also. It should not start with a numeral. It should not start with 1 or 2 or 3 and so on. It must begin with the letter. So this is a general problem which is mostly faced by the beginners. If you try to write the name starting with 1, 2, 3, there will be a problem. Or if you add a space in between the names, right? If you say that my file name is F, then space, then 1. So you cannot use space. The program will not run properly. Rather, what you can do, you can say F underscore 1, that will be absolutely fine. So it can be 63 characters long. It can contain letters, digits, and underscore. And underscore is very good for method which can be used to write the very good identifiable file names or variable names. It cannot contain punctuation characters. For example, period, comma, semicolon. It should not contain space also. Matlab is case sensitive, so if you define these four things, right, these are going to be four different variables because it differentiates between uppercase and lowercase letters. So these are four different variables. Then no spaces are allowed between characters, so better use underscore instead of space. Wherever you want to desire to use a space, better to use underscore. Then avoid using the name of built-in functions. There are some built-in functions such as we just discussed, like exp is a built-in function. So do not use a built-in function, right? Like if you say that I want to say exp is equal to 1, right? Or let's say 10, or let's say 100, right? So here I am trying to use exp, which is a keyword, as a variable name, so that may lead to some problems later on. So once a function name is used to define a variable, the function cannot be used then. Okay, there are some predefined keywords. For is for loop, then end is for ending the loop, if else if is there, otherwise you can just type help in the command window, space, and then type this keyword. You will get complete information about how to use these keywords. Function we have already discussed. Break is to stop the compiler at any location. Then case is there, catch is there, class, def, global, persistent, return. Some of the important keywords are mentioned here. Switch is there, try is there. Then there are some predefined variables also. Like you need not define the value of pi 3.14. The MATLAB compiler, it already knows it. So here, for example, in this program, nowhere pi is mentioned, right? But still, even if now, if I write pi over here, press enter, it will give me the value of pi. Because by default, MATLAB program, it knows the value of pi. It is a predefined variable. So pi is predefined. INF infinity is also predefined. ANS is the answer variable which is predefined. Do not use ANS for in your MATLAB programs variable names. I and J are also predefined to related to complex numbers. So although we can use I and J in for loops, most of the time we use, but if I talk about predefined variable, let's say if I say a is equal to 10 plus, I want to define a complex number, 10 plus 100 iota. So I write I cannot write iota complete here. I cannot write iota. So I press enter, and then you can see MATLAB understood that this is going to be a complex number. So it has converted it into a complex format where this I is treated as iota, right? Square root of -1. Similarly, if I write, let's say b is equal to 1 plus 2 j. So j is not a variable here, it is a similar to iota, so that is used to define the complex numbers. J and I both are used to define imaginary numbers, right? These are helpful in complex numbers for formation. NaN is not a number, and EPS, let us see what is the value of EPS. So you can see the answer for EPS. It is 2.2 10 raised power minus 16. That is going to be a very small value. And basically it is epsilon. Generally we talk about epsilon, and that is the value of epsilon which Matlab knows, which Matlab assumes for calculation purpose. Okay, this is the basic modal testing which we had discussed earlier. This is regarding signal processing. This we have discussed earlier. Use of band pass filters, sampling frequency effect, then effect of damping. This is an overdamped system. Sampling frequency is 50 Hz and it is increased to 100 Hz, 200 Hz. So as you increase the sampling frequency, the graphical formation, graph presentation becomes better. Logarithmic decrement, okay, this most of it we have already discussed. Okay, now we come to this. For calculation of a natural frequency, mode shapes, damping ratios, FRFs. So today we will try to see how to write a program for calculation for displaying the mode shapes. This is an FRF. This is an FRF waterfall diagram, where I think in this case I had combined more than 100 FRFs in the same diagram. Okay, now coming to the vibration analysis of beams. Here, this is the elemental mass matrix for a beam element. This is the elemental stiffness matrix for a beam element. Here, rho is mass density, A is area of cross section, capital A, that is area of cross section, and the small a is half of length of the element. Capital E is modulus of elasticity, and capital I is moment of inertia, and again the small a is half of length of element. Here M stands for mass, E for element. So this is element mass matrix. This is element, E for element, K for stiffness. This is element stiffness matrix, and these matrices are applicable for assumed to be applicable for all the beam elements contained within a particular model. And when we will be doing assembly, so we will assemble these kind of matrices, right? So here you can see this is a 4 by 4 matrix, right? So here basically let's say there is a beam element over here. It is having two nodes, one node number 2, and each node is having 2 degrees of freedom. So translational degree of freedom and rotational degree of freedom. Here also translational degree of freedom and rotational degree of freedom. So there are 4 degrees of freedom per element, right? So that is why here this is 1, 2, 3 and 4 columns, and similarly 4 rows, 1, 2, 3 and 4. So that is why this size is 4 by 4 for elemental mass matrix also, for elemental stiffness matrix also. This we have already discussed, but here I just wanted to revise. I just wanted to remind you for this, right? So now let's say there is a there is second element also. Now second element, for the second element, this will be node number 2, global numbering, and over here will be node number 3, right? Now you can see node number, if I talk about local coordinate. So for local coordinate, node number 2 for first element, that will coincide with node number 1 node second element. That means if I talk about first element, so it's local 3 and 4 degree of freedom will coincide with local 1 and 2 degree of freedom for second element, right? So based upon that, element connectivity table is also drawn, and then ultimately when you will be assembling, you will see that this is the first finite elements mass matrix. Similarly, there will be second mass matrix for second finite element also, right? And it will appear like this somewhere over here, so that degree of freedoms over here will overlap. Third and fourth degree of freedom for first element, that will overlap with first and second degree of freedom for second element. And similarly, then there will be third matrix for third finite element, and this is how over here you will see that over here there will be an overlapping within this region, and then next within this region also, and so on. For this kind of overlapping will be applicable for preparing global mass matrix as well as for stiffness matrix also. Similarly, for damping matrix also same thing will be applicable. So here is the basic program. Here I am using this CLC, clear screen, clear all, clear the workspace, clear figure window, format is short G. Then I am defining the damping constants, structural damping constants basically. Here I am assuming undamped system, so I am assuming these constants to be 0, 0. If you want to include damping, you can add some value over here. Let's say 0.0001, that is a lightly damped system. So here I want to use it for undamped system, so both the constants are 0. Constant 1 is also 0, so constant 2 is also 0. This is the length of the beam defined, this is width of the beam is defined, then thickness of the beam is defined, then density of the beam in SI units. Everything is in SI unit. Like the thickness of the beam is 5 mm. So I do not write it as 5. I write it as 5 into 10 raised power minus 3. So this 5 E minus 3, press enter. So this is basically 5 into 10 raised power minus 3. So this is 0.005 meter. Similarly, rho is also in SI units, 7.728 into 10 raised power 3 kg per meter cube. Then mass of the beam can be calculated using this simple formula. This is a very simple formula. This is basically length of the beam into width into thickness. So this is volume multiplied by mass density. So that will give you mass of the beam. Modulus of elasticity of beam is assumed to be 200 gigapascal. So that is 200 into 10 raised to power 9 SI units. Area of the beam, cross-sectional area, that is width into thickness of beam. Moment of inertia, so that is BT by 12, simple formula. So here it is width into thickness cube divided by 12. And here I am defining the number of elements. So let me expand this. Here I am defining the number of elements in the FP model. So that let's say that is 30. So in that case I can calculate depending upon number of elements and length of the beam. I can calculate A parameter A, right? Because total length is given, you divide it by number of elements, that will give you length of the element. Now A is half of length of the element, so A will be half of this. Now here I am using a function over here. Here you can see these are the outputs of the function. Its output, one output will be phi matrix. It will give you mode shape matrix. It will give you mode shape matrix. It will also give you natural frequency vector in hertz. It will also give you global stiffness matrix, and it will also give you global mass matrix. It will also give you global damping matrix, and equal to, right? This is all within the square bracket, and then I write equal to, then this is the function name, function for finding mass and stiffness matrix. Up to this is the function name. Then comes the input parameter within a round bracket. So this is a round bracket over here. Within this round bracket there are all the inputs mentioned over here. What are the inputs? That is number of elements, then this is mass density, cross sectional area, moment of inertia, half of length of beam, that is A parameter, modulus of elasticity, damping constant 1, structural damping constant 2. Now this function we will discuss tomorrow, and the output of this function is, it will give me these outputs, right? It will give me mode shape matrix also, it will also give me the frequency vector and global matrices, global mass matrix, stiffness matrix, as well as damping matrix. Now I write this equation to find out only first 5 natural frequencies in hertz. So that is done over here. So here you can see freq hertz. I take this vector and say only its row number 1 to row number 5 and first column only. And then I round it off to 2 decimal places only. So how to round the value? So you can simply write help round and enter. Right, so it mentions round to multiple of 10 raised to the power n, and the format is, the command is written in capitals for this help book, but actually in your program you will be writing it in lowercase only. Round n, square round bracket, and then x comma n, where each element of x is rounded to the nearest multiple of 10 raised to the power n. So let us see the effect. So here is an example also. Let me run this example. Copy this, paste it over here and press enter. So this example, it tells me how to round up pi value up to 10 raised to power minus 2, right? So again I repeat, upward arrow key, let's say there is a value 0.12345 enter. So it has been rounded to 10 raised to power minus 2, that is 2 decimal places. If I want to round it up to 4 decimal places, I write 4 over here, then press enter. If I want to round it up to, let's say, 1 decimal place, minus 1, I write minus 1 over here and see the effect. Let us see the effect when it is 0 also. So that will become, value will become 0, right? Let us see the effect when over here I have 100. Enter. So that is 100. Let's see the effect if I write over here 1. Let's see the effect if I write over here 2. Right? That is 100. Now let us see the effect if I write over here 3. 0. So 100 has been rounded off to 0 now. So that is basically because here I have told the compiler to round off to nearest 10 raised to power 3. That means to round off to 1000. So when I round off 100 to thousands, 10 raised to power 3 terms, then it is going to be 0. See, you are having 100 rupees in your pocket, but if I round it off to 10 raised to power 3, I can mathematically say that you are having almost 0 rupees in your pocket. You may be having 100 crore in your bank, but I reduce it to round it off to 10 raised to power 3, and mathematically it can be said you are having 0 crore rupees in your bank. So generally we use this format -2 to round off to 2 decimal places. So here also I have used the same thing. I have rounded off the frequency values to 2 decimal places only. Now here I am simply defining, in this statement I am simply defining the x-axis, and here I am mentioning the mode number to be plotted, and then I use a very simple statement, that is plot, to draw the plot, right? And another term over here is hold on. So I draw a plot. So let us see the effect first. Let me press right ZZ over here, then press F5 and see the effect. Right? This is the first mode, fourth mode which has been drawn here. Let's draw the first mode. Press F5. This is the first mode shape. Now this is after executing this statement. Now if I execute this statement, right click, evaluate selection, and now you can see the output. Geometrically it is appearing to be similar, but the y value is now smaller because everything has been, here it is multiplied by 0.2 on the y-axis. And here I have used hold on term also. Hold on means you create a first plot, then hold on, draw the second plot on the same graph, on the same paper, then draw the next plot on the same paper. Otherwise, if you do not write this hold on option, if you write hold off, if you do not write hold on, if you don't use hold on, then it will only draw the most recent one. The most recent it will show you if you run the program. So you must write this thing hold on, so that all these curves are drawn on a single graph. So let me erase this ZZ from here, and now see the effect. If I don't use hold on, now press F5. So this is the output. But if I use hold on, Control T, press F5, so this is the output. So the difference between the two outputs is, if I don't use hold on, the previous graph gets omitted, and if I use hold on, the previous graph also stays on the same figure window, and all other graphs are drawn on the same figure window. Simultaneously you can see all the graphs. So now the main thing that is left is the function for finding mass and stiffness matrices, which we will discuss later.